Let's look at how to build a circuit. So to build a working circuit, things you need to know, right? We did talk about these. You built circuits using the PhET simulation, so you should know some of the things that you need in order to have a working circuit. First of all, you need some wire. How else are you going to connect everything? Second thing is a source. You have to have a battery, some power source that's going to give those charges some energy. And the third thing is a resistance. You need some sort of resistor in there to use that energy. Otherwise, you'll create a short circuit. So you need something like an actual resistor. You need something like a light bulb or some appliance that's going to use that potential difference. Again, we've talked about this, but what would happen if the circuit didn't have a resistance? Well, we know you need resistance in order to create a working circuit. So if you didn't have a resistor, some sort of resistance, those charges would leave the battery with a ton of potential, go back to the battery with all that potential, and gain more potential. So you'd create a short circuit and you would potentially start a fire. Right? So this says without a resistance, current would flow at a maximum rate. Without a resistor, there isn't a component in the circuit to use the energy, so most of the energy would turn into heat. This would cause the wire to get very, very hot and possibly cause a fire. Other things that you may have in a circuit. You may have a switch. You may have an ammeter. Right? An ammeter is going to be connected in series. Right? Series means in one line. In another video, we'll talk specifically about series circuits. You'll also have some voltmeters, which are connected in parallel. Again, we'll talk more about things connected in parallel in another video, but you did see some of this in the PhET simulation that we did start in class together, and I talked a little bit about it in the Ohm's Law PowerPoint video. But here's your sample circuit, right? So you'll notice that there's a switch at the top that's not connected, so right now this circuit would not work. There's an ammeter, that circle with a capital A. You have a resistor, which is that squiggly line over on the right-hand side. There's a voltmeter connected around the resistor in its own branch, right, connected in parallel. And then you have a voltmeter connected around the battery over on the left. So let's talk about what the battery does. Okay, the battery essentially lifts electrons from the positive terminal to the negative terminal. Right? So remember, electrons are negative and they don't want to be close to something else that's negative. So they don't want to go to the negative side of the battery. So the battery lifts them, right, pushes them towards the negative side. And those two negative things close to each other are wanting to repel. So that gives the electrons potential, again, something we talked about in electrostatics, to do some work as they go through the circuit. So electrons are given energy that can be used to move the electrons through the circuit. Well, then what does the resistor do? So the battery lifts the electrons. The resistor is going to drop the electrons, or the resistor is going to use the energy that was gained from the battery. So you'll hear that term potential drop quite often. You'll see that, right? What is the potential drop of this light bulb, or what is the potential drop of resistor 2? And that has to do with the drop in energy that the resistor is taking away from the electrons. Something else to know. Wires that we use in a circuit have negligible resistance. So there's a little bit of resistance as the electrons travel through the wire. However, it's not enough for us to consider and calculate. As far as we're concerned, all of the energy gained from the battery must be used by all of the resistors. So as an electron travels through a circuit that has more than one resistor, some of the energy will get used in the first resistor, the rest of the energy will get used in the second resistor, and then those electrons will go back to the battery. Same thing if you had 3, right? Some would get used in the first, some would get used in the second, and the rest would get used in the third. So the thing to know is that all of the energy must be gone before those electrons go back to the battery. So how to build a circuit. There's two ways. You can wire things in series or you can wire things in parallel. So let's just quickly talk about the difference between the two. In series, you're going to wire things in one line. So essentially, there's one path for the electrons to travel through. So when you add things in series, all the resistors are placed along the same path. Here's the key. The current must flow in one line and pass through each resistor. So every single resistor is going to experience every single electron going through it, and vice versa. I guess the better way to think about it is that every single electron is going to experience each resistor. Here's an example of a series circuit. You'll notice I have 3 resistors here, right, those squiggly lines. I have 1 ammeter, and I also have a battery. So again, as a reminder, my battery, the shorter line is the negative side, the longer line is the positive side. So my negative side is on the top. Electrons are going to travel in a clockwise direction around this circuit. They'll leave the top side, they'll go through resistor 1, they'll go through resistor 2, they'll go down through resistor 3, then they'll go through the ammeter, and they'll go back to the battery. So you'll notice every electron has to go through every resistor. So here you have 3 resistors connected in series. Notice the ammeter is also connected in series. Ammeters must be connected in series to work properly. The reason for this is ammeters have a very small resistance. They're not going to change the resistance of your total circuit. They have a small resistance, so you want electrons to travel through them. The other way to build a circuit is in parallel. Okay? In parallel, each resistor has its own branch. Now, you can add more resistors in a branch, so you could have 2 resistors in one branch, but what we'll look at is a circuit where you have each resistor in its own branch. The presence of different branches means there's multiple paths where the charge can travel. So here's an example. Again, you'll notice I have 3 resistors, but these are connected in parallel. So I have the battery over on the left. Again, current is going to travel clockwise. They're going to leave the battery from the top. They'll travel along that first top wire, and then they come to a junction. Some of the electrons will travel down through that first resistor and then go back to the battery. The rest of those electrons will continue on and travel down through the second resistor, and then finally the rest of them will travel through the third. So you can see there's multiple pathways for those electrons to travel. Notice I also have 1 voltmeter here. Voltmeters must be connected in parallel to work properly. Voltmeters have a very high resistance, so electrons will not choose to travel through voltmeters. But instead, what a voltmeter is going to do is take a reading of the potential of the electron at one point and a reading of the potential of the electron at another point and find the difference between those two. So you need to know that a voltmeter has to be connected in parallel and an ammeter must be connected in series. And the reason for that is because voltmeters have high resistance and ammeters have low resistance. Okay, the last thing I want to talk about in this PowerPoint is power and energy. Right? So we've talked about power and energy when we talked about kinematics and motion, but we need to talk about the power and energy in a circuit. So we know potential difference is measured in joules per coulomb, right? That's the work per charge, V equals W over Q. This is also simplified to a volt. We also know that current is measured in coulombs per second, right? Remember, current is charge per time, I equals Q over T. This is simplified to an amp. If we multiply these two things together, a joule per coulomb times a coulomb per second, we get coulombs that are going to cancel, and we're left with joules per second. So this is energy per time, which, if you remember when we talked about power and energy, is equivalent to a watt. And watts measure what? Power. So this is equivalent to power. So what we did here was take potential difference V and multiply by I. and we came up with a unit for power. So here's our equation, P equals VI. If we substitute Ohm's law into this, now remember Ohm's law is V equals IR. So if I take Ohm's law, V equals IR, and I plug that in for V in my power equation, I come up with P equals I times R times I, which simplifies to I squared times R. If I rearrange Ohm's law and solve for I instead, and I take that I equals V over R and substitute that into P equals VI, I get P equals V times V over R, which simplifies to V squared over R. So you have three relationships for power. All three of these are on your reference table. If we relate this to energy and work, we know that power times time is equal to work. Right? That, hopefully, you remember from kinematics and energy. We can take all of our relationships for power and multiply them by time to come up with equations for work. So I have work equals power times time. And then I'm taking my first relationship for power up at the top of the screen, P equals VI, multiplying by time. So that will give me W, the work, equals V times I times T. Same thing. Add a T to that second relationship for power, so I get I squared times R times T. And then same thing for the third one. I'm going to have V squared over R times T. Those are our relationships for work. Okay. These equations hold true for materials that obey Ohm's law. So remember, if you watch the Ohm's law PowerPoint, things that obey Ohm's law are devices or resistors that have a constant resistance. Here are some practice problems, right? So there's 3 of them. I would pause the video, write them down, or at least pull out some given information, find equations, and solve. Here's our first one. Calculate the rate at which energy is supplied by a 120 volt source to a circuit with a current of 5.5 amps. Here's my given information. We're looking for the rate at which energy is supplied, right? So that's a rate, remember, is something over time, and we are looking at energy over time. What you need to know is energy is equal to work. So work over time, which is known as power. So this question is tricky because it's asking you to calculate the power, which may not seem obvious at first glance. So we're going to use P equals VI, and you get 660 watts. Question 2. If a 150 ohm resistor produces 600 watts of heat, what is the current flowing through it? So we're looking for I. We were given resistance. We were given power. So we're going to use P equals I squared times R, and you get 2 amps. Question 3. How much time will it take for a 50 volt source with a current of 5 amps to produce 30,000 joules of heat? Here's my givens. We're looking for time. So I'm going to use W equals VIT, and I get 120 seconds.